Good afternoon, everyone. So, welcome to my YouTube channel, Avatarm. So, in last lecture, lecture number 7, we have discussed what is Abel's lemma, what is Abel's theorem. So, we are going to continue Abel's theorem for uniform convergence of series. We will derive some new result from that, generalized result, more general result. Okay. So, what is that result? We are going to state. So, we are writing corollary of Abel's test. Okay. Corollary. So let P and X be sequence of function from interval I to R. I is in interval. I is interval in R. Okay. And B and X is a function from I to R. Okay. Such that B and X is monotonic for each X belongs to I. Okay. It means either it is monotonically increased for fixed I or it is monotonically decreasing. Okay. Monotonic means it is either increasing or decreasing. Okay. And there exists k greater than 0 such that B and X is less than equal to k for all n belongs to and X belongs to I. It means, what does it mean? It means the sequence B and function is uniformly bounded on I. The meaning of this statement, there exists k greater than 0 such that B and X is less than equal to k for all X n belongs to n and X belongs to I. This is in its short is called this is uniformly bounded. Okay. I have already told. Okay. If this series U and X is uniformly convergent on I, then summation n goes to 1 to infinity. B and X, U and X is also uniformly convergent on I. Okay. So this is more general result than Abel's test, because in Abel's test we have taken B and X positive, non-negative function and monotonically decreasing. Here we are not taking that B and functions are non-negative. Moreover, we are not saying that they are only decreasing, monotonic. We are saying that they are monotonic. They can be monotonic increasing as well. Okay. So let's prove this result. So we know that for each x belongs to I, b and x is monotonic function, monotonic sequence. So we know that every monotonic sequence, okay, either it is, because this is uniformly bounded as well. So what we have? We have two cases. Case one, that b and x is monotonic increasing. Monotonic increasing. If it is monotonic increasing, when I'm saying that b and x is monotonic increasing, it is monotonic increasing for each x, okay? For each x belongs to I. So if we have two cases, b and x function is monotonic increasing for each x belongs to. For second case will be monotonically decreasing, okay? So now, if this is monotonically increasing, and we know that b and x satisfy this property as it is uniformly bounded for all n belongs to n. We have taken x fixed. So what does it mean? By monotone convergence theorem. By monotone convergence theorem. Monotone convergence theorem says if you have a monotonically increasing sequence that is bounded above, then such sequences are always convergent. So this, for each x, this sequence will converge. So I am saying that limit bx, limit and tending to infinity b and x. Okay. And I am defining a new sequence. Now define a new sequence. A and x is equal to bx minus b and x. Now you check that, you can check that this sequence a and x is monotonically decreasing on I. Also, we have that a and x is greater than equal to 0 for all n belongs to n and x belongs to I. Okay. So now we can, and also we can see also that a and x is equal to bx minus b and x. Okay. So we can write it bx plus b and x. Okay. So we know that this limit b and x is bx. So it means what? This cannot go beyond k, because each b and x is less than, its absolute value is less than k. So the limit function will also satisfy this. So what does it mean? K plus k. It means a and x is, it means a and x is monotonically in decreasing sequence. It is positive, non-negative, as well as we have shown that it is uniformly bounded as well. So now we can apply here Abel's test. So this implies by Abel's test that summation n goes to 1 to infinity a and x, u and x A and X, U and X converges uniformly on I. Okay. Now observe that what is this? N goes to 1 to infinity. A and X, U and X. Now put the value of A and X. Bx minus B and X. Put here. Bx, U and X. Okay. Minus B and X, U and X. So let's say it equation number 1. Now we have to show that this B and X into U and X summation, this series is uniformly convergent. We already know that this series is uniformly convergent. If we can show that this series is uniformly convergent by sending this from left side, we can show that this is uniformly convergent. This will be uniform convergent. So it is sufficient to show that this series, it is sufficient to show that this series Bx, U and X is uniformly convergent on I. Because, okay, if we can show this is uniformly convergent, so we will send it from left hand side and we will get B and X, U and X. This is difference of two uniformly convergent series and that is convergent uniformly. Okay. So how will we show this is uniformly convergent? It is easy because let epsilon, we will show that this is uniformly consistent. So we don't, given epsilon greater than 0, because this series, since this series is uniformly convergent, and we know that uniformly convergent series is uniformly Cauchy. So this implies this series is uniformly Cauchy. They have, there exists N, capital N belongs to N, such that U n plus 1 X plus U n plus 2 X plus U n plus P X less than epsilon by 2K for all N belongs to capital N, P greater than equal to 1 and X belongs to I. Okay. For all X belongs to I. Now what about this? B Bx U n plus 1 X plus Bx U n plus 2 X Bx U n plus Px this. So you can take Bx outside. You have U n plus 1 X plus U n plus 2 x up to un plus p x. Now you see that bx is bounded by 2k. 2k. This is bounded by 2k and this is bounded by epsilon by 2. So their product will be strictly greater. So this will be for all n greater than equal to capital N, p greater than equal to 1 and x belongs to I. So this is cancel out. Okay. So we have bx un plus 1 x plus bx un plus 2 x bx un plus p x less than epsilon for all n greater than equal to capital N, p greater than equal to 1 and x belongs to I. So what does it mean? It means the what is the meaning of this? This implies summation n goes to 1 to infinity bx unx is uniformly Cauchy on I. Okay. Now we know that every uniformly Cauchy sequence is every uniformly Cauchy series is uniformly convergent. So this implies is uniformly convergent on I. Okay. Okay. Now from equation 1, we have what we have? We have this one. Okay. Now solve for this series because we want to show that this series is uniformly convergent. So we can solve it. So now you see that this series is uniformly convergent. We have already proved that. Now just we have proved that this is uniformly convergent. This is uniformly convergent. So their difference is also uniformly convergent. It means this series is uniformly convergent. So what this implies? This implies that this series dnx unx is uniformly convergent on I. Okay. So we have done case number first. Now what is case number 2? Case number 2 is that if this b and x is monotonically decreasing for each x belongs to I. If it is monotonically decreasing, okay, and we know that this B and X has this one. Every n belongs to n. For all. So we know that by monotone convergence theorem. There is another statement of monotone convergence theorem. A monotonically decreasing sequence which is bounded below is always convergent. So we have taken the limit bx. Again you take limit this. Okay. B and x. Okay. So this is monotonically decreasing. Now what we will do? We will define a new sequence. A and x is equal to b and x minus bx. Now you see that, observe that A and x is monotonically decreasing for its x belongs to I. Also, we have this one. Also, you see that A and x is equal to B and x minus bx is greater than equal to 0 for each x belongs to I. Sorry, for n belongs to n and x belongs to I. Okay. Also, by using same technique, what is we have? A and x is less than equal to 2k. Similarly, we can show it as we done in case number 1. Now, so we have again applying. Now we can follow the same process as we have done in case 1. Okay. What we have done by Abel's test, this series goes to 1 to infinity. A and x, u and x is uniformly convergent. Okay. This is uniformly convergent. Now, next, but this series is nothing but solve this series. Put the value of A and x. Now you can show that in a similar way as we have done in case first, that this series is uniformly convergent. Same technique. And we already know that this is uniformly convergent. So we will bring this series here. This will be in sum. Then what will we have? So I am writing directly that this series is, because we have done same technique, use same technique, same process in case number first. So this implies this series B and x, U and x is uniformly convergent on I. So we have done the corollary. Okay. Now we will do some questions. Okay. Question. Okay. Let this series AN converges uniformly on okay minus 1 to 1. Okay. 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 This series converges uniformly. Is the series n goes to 1 to infinity a n x x to the power n converges converge is sorry does the series converges uniformly on minus 1 to 1. Whether this series is convergent? I am asking this question. Okay. So we will see it. Okay. Solution. So we have this series. Now, what is my BNX? BNX is this on this interval. You take any x from this side, you will find for any x belongs to this interval. We have BNX is monotonically increasing. Okay. For any. Okay. Also, you see that I can, it will be always less than equal to 1 because we are taking this one. Because this is equal to and that is less than equal to. So this implies B and X sequence is uniformly bounded for all n belongs to n and X belongs to. So this implies this sequence is uniformly bounded on I. Okay. Now, by corollary, we have this series n goes to 1 to infinity a and x to the power n is uniformly convergent on minus into. Okay. Now we are seeing second question. Question number 2. I am writing again. Let this series summation n goes to 1 to infinity a n x is uniformly convergent on -1 to 1. Does the series summation n goes to 1 to infinity a n x x upon 1 plus x and xn x to the power n converge uniformly on this interval? Okay, so we'll solve this. Okay, also. So how to solve this? Solution. Now see this a n x into x to the power n 1 plus x to the power n. So what is my b n x here? This function. Now see that what is this? Whether this is uniformly bounded or not. So I can write always like this. Okay. Okay. Sorry, you write this x to the power 2n. 2n is here. Okay. 2n. 2n is here. 2n. Okay. So what is this? So x to the power 2n I can also write like that. Okay. Now see that this is always less than this one. But this is always bounded by 1. Okay. So we have b and x is less than equal to for all n belongs to n and x belongs to -1 to 1. Okay. So this implies Bn is uniformly bounded on -1 to 1. Okay. Now what about whether this Bnx is increasing, decreasing? What about this one? Okay. What about this sequence? Okay. So fix x belongs to -1 to 1. Then what is b and x is equal to x to the power n 1 plus x to the power 2n. Okay. As you see that when x is in this range, so x to the power n is for fix x to the power n is increasing function. Okay. increasing function. Increasing function in -1, 0. Okay. Increasing function. Okay. Increasing function. See, sorry, we want to change this question little bit. We want to change the interval. We want to take this interval here. And interval is this. Close interval 0 to 1. So we are asking this question. Okay. Now see this is bounded by 1. Okay. So erase here. Okay. So 0. Now you take any x is in this range. So you take power. Power will always decrease magnitude. So it will be, suppose you are taking -1 by 2, you take power 1, then 2. So it will be, its magnitude will be decreased. Once magnitude is -1 will decrease, it is increasing. So this quantity is increasing. Increasing function on this interval. Okay. On this interval. Okay. And because this is, and similarly, this function, similarly, if we take this function x to the power 2n, this function is decreasing function. Function on -1 to. If this is decreasing, if this function is decreasing, what does it mean? It means that this function 1 upon 1 plus x to the power 2n function, x to the power 2n function is increasing. X to the power 2n is increasing function. So you take product of two increasing function, that is also increasing function. So this implies that product of two increasing function is increasing. This implies b and x is equal to product of two increasing function is increasing. So x to the power n into 1 plus x to the power 2n is also, this is b and x is increasing function. This is increasing function and uniformly bounded function. Okay. So by corollary, what you have? By corollary, This implies by corollary we have that this series n goes to 1 to infinity a n x to the power n 1 plus x to the power 2n converges uniformly on -1 to 0. Okay, so we have done two examples. So in today's lecture, what we have done, we have seen a consequence of Abel test, and we are saying it's corollary of Abel test, and we have proved it. Okay, and we have done two examples on it. Okay, so thank you very much for today's lecture. Kindly like, share, comment, and subscribe my YouTube channel. If you have any problem related to this session, you can give me a comment on my YouTube channel. I will take care, and I will discuss in next session. So thank you very much for today's lecture or session. Thank you very much.